In this video lesson, I'll be teaching you how to determine the eigenvalues and eigenvectors of a given square matrix. I shall also teach you how to verify the Cayley-Hamilton's theorem of a given square matrix. Here on the board, we have this question based on a 2x2 square matrix. After handling this, we shall move on to see problems on a 3x3 square matrix. So, come along, let us see how to solve this problem. Find the eigenvalues and the corresponding eigenvectors of Ax equal to lambda x. This is a powerful equation, a matrix equation used when dealing with eigenvalues and eigenvectors. And of course, it extends to dealing with Cayley-Hamilton's theorem as well too. Okay, so this is the equation whose eigenvalues and eigenvectors we are asked to find, where A is the matrix given as 2, 3, 4, 1, a 2x2 square matrix. Now, how do we go about solving this problem? The first thing we need to do is to obtain the eigenvalues. So the question could be, how do we get the eigenvalues? Remember that I explained previously that to obtain the eigenvalues, we need to solve the determinant of the characteristic equation when it is made equal to 0. What is the characteristics equation? Okay, let's bring out the matrix given A to be equal to 2, 3, 4, 1. The characteristic equation is given as, we have it to be A minus lambda I. This is the characteristic equation. Its determinant made equal to 0. So all you need to do is to solve this equation you have there on the board. Get the determinant of A minus lambda I when it is made equal to 0. And what does the I there represent? Because of course the I is not here. The I is not in this equation. I here represent unit matrix. Unit what? Matrix. You can also call it identity matrix. And the reason for us multiplying this lambda with I is because this lambda is a scalar, is a constant, a number. And you cannot subtract or add a number, to a matrix. That A there is a matrix. So you can't subtract this lambda from it directly. Therefore, you need to convert that lambda, that scalar, to a matrix. And the only way we do that is multiplying it by a unit matrix I. And that unit matrix, like I also explained previously, must have the same order as the matrix. Remember to add or subtract matrices. The two or more matrices you are adding or subtracting must have the same order. So if A is a 2x2 square matrix, I must also be a 2x2 square matrix. And now if A is a 3x3 square matrix, what do you think the identity matrix, the unit matrix would be? Good. A 3x3 unit matrix. We shall solve this equation and obtain the value of lambda. That value of lambda is simply what we call the eigenvalues. I don't believe you are ready, so let us do this and see. We shall obtain the value of A minus lambda I first. Is that okay? So let me write here I is equal to unit matrix. In this case, it's going to be a 2x2 square unit matrix. So it's going to be equal to 1, 0, 0, 1. This is the unit matrix for a 2x2 square matrix. If it is a 3x3 square matrix, it's going to be 1, 0, 0. You go to the second row, 0, 1, 0. You go to the third row, 0, 0, 1. Just like echelon row reduced matrix. We studied that in linear algebra anyway. Let's focus on our business here. The identity matrix I is equal to this. Reason, because we are dealing with a 2x2 square matrix. So substituting it into this A minus lambda I, we shall obtain our A is 2, 3, 4, 1. So this is going to be minus lambda times 1, 0, and then 0, 1. Good. This term you are seeing here is the same as lambda times 1, which will give you lambda. And then lambda times 0, which will give you 0. Then lambda times 0 here, 0, and lambda times 1, which will give you lambda. Let me write it out. Subtracting this is going to be equal to, let's say, the matrix you are going to get. If you're subtracting matrices, you pick the corresponding element to corresponding element. What do I mean by that? element in row 1 column 1 of the first matrix minus or plus element in row 2 in row 1 column 1 of the second matrix. Then after that, you move on to element in row 1 column 2 minus element in row 1 column 2 of the second matrix in that order. So we go 2 minus lambda will simply give us 2 minus lambda like this, you know. Then 3 minus 0 will give us 3. 4 minus 0 will give us 4. 1 minus lambda will give us 1 minus lambda this way. This term, 2 minus lambda, 3. 4, 1 minus lambda is the value of A minus lambda I. Now remember, to obtain the eigenvalues, you are asked to solve the determinant of that term, A minus lambda I, when it is made equal to what? 0. Since we've known the value of A minus lambda I, we shall obtain the determinant now. Is that okay? So we want to get the determinant of this term. We have 1 minus lambda. Alright? This slash sign simply means determinant. So we are going to make this equal to 0 while obtaining the determinant. So, how do we get the determinant? We've studied that previously as well too. It's going to be this term times this minus this times this. You always start from top left corner times, you come down to down right corner, minus, you come to down left corner times up right corner. Please take note, although we are still going to see something like that for 3 by 3 square matrix, you know, you have 3 rows. How we handle that first, you're going to put plus, minus, plus in the first row. Then you do some deleting of rows and columns and then solve the determinant, okay? When we get there, we'll cross it. Let's focus on this. Obtain the determinant of this. This is going to be equal to 2 minus lambda times 1 minus lambda. So I have this, then 1 minus lambda, then minus, this term together, minus this times this, which will give us 12. Make it equal to 0. All that is now left for us is to solve this equation, and I will be pretty fast in doing that. Let us expand this term. If we expand this, we are going to get 2 times 1 giving us 2, and then minus 2 pi, and then minus 2 lambda rather, and then minus lambda plus squared lambda, then minus 12 equal to 0. This eventually will give us squared lambda minus 3 lambda. 2 minus 12 will give us minus 10 equal to 0. Let us factorize this equation quickly. First, use the coefficient of this lambda square, okay, to multiply the constant term. That's how you approach factorizing a given quadratic expression or quadratic equation. Is that okay? Now, this is 1. 1 times minus 10 will give us minus 10. Then you find 2 numbers which are factors of minus 10, such that if you add these 2 factors you're talking about, it will give you minus 3. And observing this, I guess 5 and 2 will be suspected as the numbers that can do that for us. What is now left is for us to think of how to arrange the signs of that 5 and 2. And clearly, if we have minus 5 and plus 2, minus 5 times plus 2 will give us minus 10. And then, minus 5 plus 2 will give us minus 3. So that satisfies the equation. Now that we know that minus 5 and plus 2 will solve this problem for us. How do we now get the value of lambda? It's simple. Therefore, lambda is equal to, now listen, that minus 5, change the sign. Because here now the factors we are talking about here is simply lambda minus 5 and then lambda plus 2. Divided by 1, divided by 1. Place this minus 5 is over 1, this 2 is over 1. Because of the coefficients of this lambda squared. Anyway, we've already said that minus 5 and plus 2 will do the work for us. So to get the root of this equation, which are the values of lambda here, which of course happens to be the eigenvalues we are looking for, all you need to do is to change the signs of those numbers, those factors. Minus 5 will change to plus 5. Then plus 2 will now change to what? Minus 2. So this is going to be lambda equal to 5 or minus 2. These are the roots of this equation. They are the characteristic roots we are looking for, the eigenvalues. Therefore, the eigenvalues are, I can decide whichever of them to call lambda 1 and the other lambda 2. The choice is mine. Please take note that I can decide to say lambda 1 is equal to 5. and lambda 2 is equal to minus 2. Is that okay? The choice is yours. These are the eigenvalues, and that's how simple we obtain eigenvalues. If it is a 3 by 3 square matrix, you go by the same principle. Are you following? The only thing is that the unit matrix, identity matrix, will become a 3 by 3 identity matrix, which I told you earlier. And then sometimes when you're working it out, you get a polynomial which you factorize. It's simple. At this point, we shall now move on to obtain the eigenvectors. To get the eigenvectors, we need the eigenvalues. Are you following, right? We shall now move on to obtain our eigenvectors. For the eigenvectors, we shall deal with ax minus lambda x equal to 0. What have I done? In this equation, I've moved lambda x to the left-hand side. And then if you factorize your x, you're going to get a minus lambda multiplied by x equal to 0. You cannot subtract a scalar from a vector. You cannot subtract a scalar from a matrix. Therefore, what do? You have to multiply this lambda once again by a unit matrix. This implies that a minus lambda times I multiplied by this x. This x is a column matrix, or a column vector as you might call it. A column vector, just one column. Is that clear? And of course, the values of this x are what we refer to as the eigenvectors. So our interest here now is to solve and obtain the value of this x. That gives us the eigenvectors. So here we're going to make this equal to 0 and solve to see what this is going to give to us. Take note, this lambda has two values now. This lambda is the eigenvalues, right? And you know that there were two values that we obtained as eigenvalues. One is 5, the other is minus 2. So we shall use both of them to solve and obtain the value of this column vector, x, where x is equal to a column vector. Since this is a 2 by 2 square matrix, then the eigenvectors you're going to get will be 2. And so we're expecting to get something like x1 and x2. Remember I said this is a column vector, and this is how it's going to look like. So our aim is to obtain x1 and what? x2. Remember, these are our eigenvectors. And of course, there are two values we are expecting here, because the matrix we're dealing with here in this question is a 2 by 2 square matrix, which means if we're to deal with 3 by 3 square matrix, then the eigenvectors is expected to be 3. I don't know if I'm communicating here. Of course, the eigenvalues will also be 3 in that case for a 3 by 3 square matrix, which means that the vectors will also be 3 of them. Please, let's proceed and solve this. For the eigenvalue lambda 1 equal to minus 2, we'll substitute it into this equation. This is going to give us a minus lambda 1, and that lambda 1 is of course 2, minus 2 here. So let me just fix it, and then for you to see it clearly. Multiply by x equal to 0. I can still simplify this. This is the same as a minus lambda 1 is minus 2. If you fix minus 2 for this lambda 1, this will become minus minus. And minus minus we change to what? Plus 2i multiplied by x and make it equal to 0. Let us now substitute the matrices here and see what we're going to get. Matrix A is 2, 3, 4, 1. We are adding it to matrix 2i. Are you following, right? Which is going to be 2 times the unit matrix 1, 0, 0, 1. We're going to multiply this whole term by x, make it equal to 0. Taking note that we are solving for what? X. This is matrix addition. It's a simple thing. 2 times 1 will give us 2, 2 times 0 will give us 0, 2 times 0 will give us 0, 2 times 1 will give us 2. Which means that this matrix is actually 2, 0, 0, 2. So we are adding this to it. 2 plus 2 will give us 4. And then 3 plus 0 will give us 3. 4 plus 0 will give us 4. 1 plus 2. Remember this is 2 because this 2 is going to multiply. 1 plus 2 will give us 3. And then we'll multiply by x, make it equal to 0 once again. So let's do that and see. Adding up this, we are going to get 2 plus 2, giving us 4. And then we have 3 plus 0, giving us 3. Second row here, 4 plus 0 is 4. And then 1 plus 2 will give us 3. Multiply this by x. Remember our x is a column vector I said already, so let me introduce it. x1 and then x2, make it equal to 0. This is matrix multiplication now, right? So let us multiply this matrix and see. 4 times x1 plus 3 times x2. If you do that, you're going to get 4x1 plus 3x2. That will be equal to 0. Once again, we go to root 2 and do same. 4 times this plus 3 times this. Of course, you're going to get the same equation essentially. Also, we have 4x1 plus 3 times x2 giving us 3x2, again equal to 0. Since they are the same equation, we are simply going to pick one of them. Is that okay? We are simply going to pick one of them. This is simply 4x1 plus 3x2 equal to 0. And hence, what do we do from there? We are going to solve in terms of x1. We're going to solve in terms of what? x1, which means we'll make x2 subject of the formula from there. Making x2 subject of the formula, x2 is going to be equal to minus 4 all over 3 times x1. You know, this 4x1 will cross, becoming minus 4x1, then you divide through by 3, the quotient of x2. And that makes x2 subject of the what? Formula. At this point, what do we do? I am going to write this term as a ratio of both sides, so that this will become x2 divided by x1. I divided through by x1, are you getting me right? And then that is equal to minus 4 all over 3. This thing I did here is simply telling us that x2 is equal to minus 4 and x1 is equal to what? 3. That is the interpretation of what I've done here. We can now conclude, therefore, x, which is equal to x1, x2 as a column vector is equal to x1, I said is 3. You can say that this is numerator, this is numerator, so x2 is equal to minus 4. This is denominator, this is denominator, so x1 is equal to 3. Fixing that up here, we have 3. And then x2 is minus 4. This is our first eigen vector. I'm going to indicate, therefore, for lambda 1 equal to minus 2. The eigen vectors are x1, x2, which gives us 3, and then minus 4. Good. We have successfully obtained the value of the first eigen vector. Please take note of something from here, because this equation we obtained here simply is telling us that x1 can have infinitely many solutions. As a matter of fact, let me do a rough work here. Rough. To show you something, because what I did here is just to go directly and quote what our answer is expected to be, or per se, how we usually quote our answer. Ordinarily, this is what happens. At this point, we can select a value for x1, any value of your choice. But generally, for convenience, we use x1 to be equal to 1. That is, we select 1 to be our x1. If x1 is equal to 1, it implies that x2 will be equal to minus 4 divided by 3 times 1, and then x2 will be equal to minus 4 over 3. I'm trying to show you something, the real working. What I did here is just to quote the answer directly, and of course, that is expected. That's what we expect when dealing with this. But in reality, this thing is telling us that x1 and x2, like these eigenvectors, the solution of this matrix we are dealing with, has infinite solutions. Are you following, right? It's a non-trivial case. Now, collecting this, you're going to get x to be equal to x1, x2, which of course will give us our x1, we say let it be 1, and then x2 we obtain minus 4 over 3. At this point, we will do a scaling up, multiplying x1 and x2 by the denominator that we have there. And the denominator we have there is 3. If you multiply x1, so x1, x2 will now be equal to, if you multiply this 1 by this denominator 3, you get 3. And if you multiply this minus 4 over 3 by 3, you know, you are going to get minus 4. So you see it is the same as what we obtained here. So in theoretical cases, we have to go through this direction from here. Is that clear? But in objective case, simply move on straight, express this as a division sign, and then you get your x1 and x2 directly this way. Like I said, in theory situation, you are meant to do this from here. Is that okay? Now, we shall obtain the eigenvectors for the second eigenvalue, lambda 2 equal to 5. For the second eigenvalue, we can obtain the corresponding eigenvectors. Let's find out. Lambda 2, we got it to be equal to 5, right? So with this, all we need to do is to go back to our equation. Already you saw how I simplified it to get A minus lambda I. Of course, this time around is going to be lambda 2I. Okay, so let's go straight. We are multiplying this by x and then making it equal to 0. Where of course x is our what? Yeah, x is the eigen vector we are looking for. The value of x will give us the eigen vectors, okay? And so we shall substitute directly and see what we are going to get here. A is 2, 3, 4, and 1. And remember, we are subtracting lambda 2i from it, and then lambda 2 is 5. Our I is 1001. All of this term will be multiplied by x and then equated towards 0. Let's solve out this and see. Remember once again, this is 5 times 1 giving you what? 5. 5 times 0, 0. 5 times 0, 0. 5 times 1, 5. So we are subtracting that from this. Let's go straight on and see. 2 minus 5 is going to give us minus 3. And then next, 3 minus 0 will give us 3. And then in the second row, we have 4 minus 0, which will give us 4. And then 1 minus 5. 1 minus 5 is going to give us minus 4. We are multiplying this by x and then equating towards 0. And remember, our x is a column vector, whose value we call the what? Eigen vectors. So let us substitute and see. It simply implies that minus 3, and then 3, 4, and minus 4 multiplied by x1, x2 will be equal to what? 0. At this point, we are going to multiply these matrices and then solve for x1 and x2. Minus 3 times x1 will give us minus 3x1, and then plus 3 times x2, which will give us plus 3x2. And of course, that is meant to be equal to 0. Take note once again, this 0 you're seeing here can still be written as a column vector 0, 0 this way, if you want. Are you following? Then enclosed in a bracket as a matrix on its own. Just telling us that this is a homogeneous system. All of these concepts, we encounter them in linear algebra. Let us proceed, please, to deal with this question. I am done multiplying row 1 times this column 1. This time around, I'm moving to row 2 times this column 1. And I'm repeating the same thing. So we have 4 times x1, which will give us 4x1 plus minus 4 times x2. Of course, minus 4 times x2 will give us minus 4x2, which means this plus will change to what? Minus 4x2 equal to 0. This particular one is interesting. You notice that the two equations we got there are no longer the same. Like what we saw when we solved for the eigen value, lambda 1 equal to minus 2. Remember, for that one, the two equations we got are the same thing. And so we used just one of the equations. But in this case, they are different. Okay? So what do we do from here? We are going to solve for this equation and see what we are going to get. Although any one of them you use, you still get the same result. Is that okay? If you like to use this first one to get the value of x2, or you decide to use this second one to get the value of x2, the answer you're going to get will be the same. Let's call this equation 1 and this equation 2. So using any one of them, since they contain the same variables, from equation 1, I have minus 3x1 plus 3x2 equal to 0. I'm going to solve in terms of x1. So I'll be making x2 subject of the formula. Making x2 subject to the formula, minus 3x1 we cross to give us plus 3x1, and then I'll divide by what? 3. And so this implies that x2 is equal to x1. Are you seeing that? x2 is equal to what? x1. Now if you want to arrange these in a form of division, just like I did previously, we can divide through by x1. If I divide through by x1, I'm going to get that x2 divided by x1 is equal to, watch, if you divide here by x1, you get this. Divide here by x1, x1 will divide x1 to give you 1 over 1. I hope you know that, right? Take a look. If you have x1 divided by x1, this will divide itself gives you 1, this divide itself gives you 1. Are you following? So this is eventually 1 over 1. And 1 over 1 will still give us 1, but I don't want to write it as 1. Because I want to bring my result out for values of x1 and values of x2 as a column vector. Therefore, x, which is equal to x1, x2 as a column vector, will be equal to 1 and 1. Does this make sense? And we have obtained our eigen vector for lambda 2 equal to 5. Let's conclude. Good. So you see for lambda 2 equal to 5, the eigenvectors that we've obtained is simply 1, 1. And this is how we are done with solving this problem. So you see, it's pretty a simple concept. Are you following, right? You can rewatch the video and, of course, grab the concept very well so that you don't make mistake while dealing with it. We are now presented with a 3 by 3 square matrix, and it is expected that we determine the eigenvalues for the equation Ax equal to lambda x, where A is the matrix 2, 1, 1, 1, 3, 2, minus 1, 1, 2. And of course, the next part of the question, we are expected to obtain the corresponding vectors, of course, eigenvectors, to each eigenvalue that we will obtain from this question number 3 here. Now, this problem is essentially similar in the way we handle it to the one that we solved previously in question 1. The only difference is that this is a 3 by 3 square matrix. Hence, we're going to be pretty fast in handling this because we already have laid the foundation. Shall we do this together, please? Now, the matrix given to us is A equal to 2, 1, 1, 1, 3, 2, and then minus 1, 1, 2. Recall, to obtain our eigenvalue, we need to solve this solution to question number 3. We need to solve a characteristic determinant equation. Alright? So I'm going to write, recall, we need the determinant A minus I lambda equal to 0 in order to obtain the eigenvalues. Of course, before we proceed to get the determinant, we need to obtain the value of A minus I lambda, where I is a unit matrix. This time around, the unit matrix is going to be that of 3 by 3 square unit matrix. And so substituting, we are going to get A minus I lambda. Our A is 2, 1, 1. Then our 1, 3, 2. We have minus 1, 1, and 2. Subtracting I lambda. I is going to be 1, 0, 0. 0, 1, 0, and 0, 0, 1. You have to memorize that. Are you following, right? Unit matrix for a 3 by 3 square matrix. Remember, this has to be multiplied by lambda. So I have my lambda here. Now let us work it out and see what this is going to give to us. This is equal to 2 minus lambda times 1. Lambda times 1 will give us lambda. So 2 minus that lambda is going to give us 2 minus lambda this way. Then 1 minus lambda times 0 is 0. Then 1 minus 0 will give us 1. And we have 1 minus lambda times 0, and that's going to give us 1. Alright? So we're going to do the same thing along the line. Going to row 2, 1 minus lambda times 0 will give us 0 here, you know. 1 minus 0 is 1. Working on row 2 now. And then 3 minus, this will now become lambda, you know that. Because minus lambda times 1 will give us that minus lambda. So 3 minus lambda is what we're going to get there. 3 minus lambda. And of course, 2 minus 0, which will give us 2. Move on to row 3. In row 3, we have minus 1. Minus lambda times 0. Here is 0 already. So minus 1 minus 0 will give us minus 1. And then 1 minus 0 here will give us 1. Finally, 2 minus lambda, because this lambda times 1 will give us lambda. Then 2 minus lambda, we have our 2 minus lambda there. So this is the value of A minus lambda I. This is the value of A minus lambda I. Let me indicate it. A minus lambda I. Because this is our A, this is our lambda, and this is our unit matrix I for a 3 by 3 square matrix. We shall now obtain the determinant of this term. So we're solving for determinant of A minus lambda I, which we've already obtained the value of A minus lambda I. So I'm going to work out the determinant. This is 2 minus lambda. This is 1. We also have 1 here. Then row 2, this is 1. 3 minus lambda. Then this is 2. And row 3 minus 1. Then we have 1. And 2 minus lambda. This is expected to be equal to 0 if you obtain the determinant of that equation, okay? So we equate it to 0 and then obtain the determinant of that term. So we go. How do we get the determinant of this term? This is a 3 by 3 square matrix. Therefore, this will become plus, minus, and then plus. Okay? Plus, minus, plus. And so, we are going to keep these 2 minus lambda constants. You know how we handle a 3 by 3 matrix if we want to get the determinant. Alright, so use your eye of imagination to delete the column and the row of that 2 minus lambda that you kept constant. We will be left with 3 minus lambda, 2, 1, 2 minus lambda. And so we will obtain the determinant from there. 3 minus lambda times 2 minus lambda. Of course, that's going to give us 3 minus lambda in brackets times 2 minus lambda. It is not usually ideal when you are dealing with these, okay, to expand this, maybe working it out here. You can just leave it in this form, okay? Along the line, if it becomes necessary to expand, you expand it, okay? But for now, we're just going to move on straight. Then minus 1 times 2, which will give us 2. Good, we are done with this 2 minus lambda. I shall pick minus 1 now, so this becomes minus 1. Of course, you have to delete the rows and column of that minus 1 using your imagination. If you do that, you'll be left with 1 minus 1, 2 and 2 minus lambda. So we go 1 times 2 minus lambda will give us 2 minus lambda. Then of course, it's meant to now be minus, you know, the follow come minus when you're solving determinant. Minus, then we have minus 1 times 2. This minus 1 times 2 will give us minus 2. But remember there is a follow come minus here. So minus minus will now change to plus 2. So this becomes plus 2. Finally, we are going to pick plus 1, keep it constant. And then of course we do the same thing. Delete the column and the row of that plus 1. You'll be left with 1, 3 minus lambda, minus 1, and 1. And then you solve the determinant. 1 times 1 will give us 1. And then minus, remember the follow come minus when solving determinant, minus, then what? Minus 3 times, oh no, minus 1 times 3 minus lambda. You know, this minus 1 times 3 minus lambda will give us minus 3 minus lambda. Now that minus you obtain from this multiplication will now go by saying minus minus 3 minus lambda, which eventually becomes plus, open bracket, 3 minus lambda. Okay? Don't forget, when you're solving determinant, there is always a follow come minus. When you do this times this, minus this times this, alright? So if there is, when you want to do this multiplication, if the result gives you negative, eventually you're going to get minus minus, which becomes plus. Okay, let's move on please. Working this out, we are going to get this to be equal to 0. It implies that we can open up this bracket please. I want you to watch this quickly, let's work it out. If you open up this bracket here, this inner bracket, you're going to get 2, alright, plus 2. And 2 plus 2 will give us 4, minus lambda. Then minus 1 times that 4 minus lambda you have in bracket will simply give you minus bracket 4 minus lambda. Please permit me to work it out here. This is going to give us minus open bracket 4 minus lambda. That's what we're going to get there. What about this one? Let's watch and see. You know, there are too many terms here, so I don't want to touch that yet. Let's watch this and see. If you open up this inner bracket, you get 1 plus 3 minus lambda. 1 plus 3 is going to give us 4. So eventually this term will also give us 4 minus lambda. Positive, okay? Positive because this one here is plus. So you have plus 4 minus lambda here, and this one gives us minus 4 minus lambda. Plus a number minus that number is equal to 0. So this guy will give you 0. This one will also give you what? 0. Because this and this, are you following right? It's just like saying 2 minus 2, you get 0. So plus 4 minus lambda minus 4 minus lambda is equal to 0, they go off. We are left with this term. It implies that we now have 2 minus lambda in brackets. I'm opening up this bracket now using this 2 minus lambda, okay? So this 2 minus lambda times this term. I want to write it this way. Then remember that this 2 minus lambda will also multiply this term. And if it multiplies, you get minus 2 brackets 2 minus lambda. Everything equal to 0. Good. Let's be pretty fast now. If you look at this term and this one, something is common to both of them. You know, this term and this term. 2 minus lambda is common, so we can factorize it out. 2 minus lambda is common. Having pulled it out, we will now be left with, remember from here you pulled out 2 minus lambda, so you'll be left with 3 minus lambda. You'll be left with another 2 minus lambda. Remember, here we have two of them, so I just pulled out one. So this 3 minus lambda will be left, 2 minus lambda will be left. Good. And then coming here, this 2 minus lambda was also pulled out, so you'll be left with minus 2. So I'll fix that minus 2. And then make it equal to what? 0. We are moving. This becomes something like saying x plus a in brackets times x plus b in bracket equal to 0. You know, if you meet something like that in quadratic equation, you pick one of them equal to 0, pick the other equal it to 0. So this simply means that 2 minus lambda is equal to 0, or this whole term, 3 minus lambda, bracket 2 minus lambda, then minus 2 is equal to 0. We can simplify this at this point. This simply means from here, okay, that lambda is equal to 2. That's from here. Or we can say from this part, if you expand this term, we are going to get minus lambda times minus lambda will give us squared lambda, and then the term that will get lambda raised to power 1. Please take your time to do the expansion here yourself, okay? But this eventually will give us something like minus 5 lambda, and then plus 6. That plus 6 from here minus 2 will give us plus 4, equal to 0. We can concentrate here and factorize now. We have already gotten one value of lambda, the eigen value, one of them. It's just for us to solve this quadratic equation now and get the other two. And I'm going to break it down here. If you factorize this term, two numbers, which if you multiply, you get plus 4. And then if you add, you get minus 5. The numbers are 4 and 1 with signs. It's going to be minus 4 and minus 1. When you multiply minus 4 minus 1, you will get plus 4. And if you add them, minus 4 minus 1, you get minus 5. Therefore, what's going to be the value of lambda from here? It's simple. Change the signs of that minus from minus 1. And so we have lambda is equal to 1, or lambda is equal to 4 from this part. We are done. Therefore, the eigenvalues becomes can now say lambda 1 is equal to 1. I'm taking this to be lambda 1. It's my choice. Is that okay? And then lambda 2, I'm picking this. And then lambda 3, I am picking this. You may look at this and say, oh, I picked lambda 1, lambda 2, lambda 3. You know, considering the magnitude of these answers I got. No. I can decide to say lambda 1 is equal to 4, lambda 2 is equal to 1, and lambda 3 is equal to 2. The choice is mine. Is that okay? Alright, so this is good. This is good. If you want, you can put it, you know, in coordinate form, or one can simply say that lambda is equal to 1, 2, 4. Is that okay? The choice is yours. However I want to present it. But it's important to know if it is in objectives, your examiner will decide the format to present the option. You go by that. Is that okay? Alright, having obtained our eigenvalues, we shall now use each of them to obtain the eigenvectors, which takes us to question number 4. Alright, now the eigenvector, the fourth question here, alright? Recall that I stated earlier that if you want to obtain the eigenvector, you are expected to solve the equation. Right, this is question number 4. So you're going to recall a negative, that is a minus lambda I, multiplied by x, where x is the column vector, the eigenvector we are looking for. That's equal to 0. X is equal to x1, x2, x3. Yes, this eigenvector we are looking for this particular question, remember that the eigenvalues we obtained, lambda 1, lambda 2, lambda 3, each of them will produce an eigenvector. Now the eigenvector will span over these values, x1, x2, x3, will generate these values, x1, x2, x3. That's what I mean by span. Is that okay? SPAN. How did I get to know that these eigenvectors are going to be x1, x2, x3? Because we are solving a 3 by 3 square matrix. I think I said that earlier when we solved the previous question on 2 by 2 square matrix. Therefore, we are going to substitute this into this equation now and solve for each of the eigenvalues. Guess I should write here. So now say for lambda 1 equal to, okay, I think I used 1 to be the value of lambda 1. This simply means we come to this equation and substitute. Matrix A is given to us already 2, 1, 1, 1, 3, 2, minus 1, 1, 2. Minus, this is lambda I, and of course our lambda 1 here is 1 times the unit matrix. a 3 by 3 unit matrix, 1 0 0, 0 1 0, and then 0 0 1. I am going to multiply all these terms by x1, x2, x3, and then equate it to 0. So this is what we're dealing with. I only substituted into this equation, so it's nothing difficult. Is that okay? Here you are going to do your matrix subtraction and multiplication. Then you make it equal to 0. I told you that this 0, if you wish, you can write as 0, 0, 0. Like a column vector. The choice is still yours. So let us move on, please, a bit fast. This one multiplied by this, you still go to this unit matrix. So I'm going to go straight. 2 minus 1. 2 minus 1 there is going to give us 1. Then 1 minus 0, we have 1. 1 minus 0 again will give us 1. Then we have 1 minus 0, which is 1. 3 minus, this is going to be 1, you know that. So 3 minus 1 will give us 2. And then 2 minus 0 will give us 2 again, alright? Then we'll move to the third row. Minus 1 minus 0. Because minus 1 minus 0 will give us minus 1. And then 1 minus 0, again we have 1. And then 2 minus 1. And 2 minus 1 will give us 1. Good. We've obtained this value, this subtraction. And so we're going to multiply it by x1, x2, and x3. This is equal to 0. Let's do a multiplication now quickly. This times this, plus this times this, plus this times this. That implies that we have x1 plus x2 plus x3. That will be equal to 0.